We've spent the last few days talking about impulse. Impulse is the change in momentum experienced by an object, or two objects, or three objects in a system. Today I want to talk about not the individual objects like we have over the last few days, but rather the system itself, all of the objects together. Before we do that though, we have to talk about a new term, an isolated system. An isolated system is a system in which there are no external forces acting. That means there's no air resistance acting, there's no friction acting, or any other forces, or at least we're analyzing the problem before those forces have a chance to act. So maybe we're looking at a collision immediately before the collision, immediately after the collision, so that friction hasn't had a chance to kick in, or air resistance hasn't had a chance to kick in. If we have an isolated system, a system in which there are no external forces, then the total momentum, that is of all of the objects combined, will always remain constant. In other words, momentum will be conserved. That doesn't mean that the momentum of each individual object will stay the same, but the momentum of the system will stay the same. Now, when are we going to use this to solve a problem? Well, we're going to look at two situations, two general situations. One where we have a collision, and that's pretty self-explanatory. Two cars collide with each other at an intersection, or two people collide with each other on a football field, or an explosion. That's not necessarily a literal explosion like a bomb blowing up, or it could be, but it could be something as simple as firing a gun. The gun goes one way and the bullet goes the opposite way, or standing on ice and throwing a ball. The ball goes one way and the person throwing the ball goes the other way. We could consider that to be an explosion. If we have a collision or something like an explosion, then we can look at the momentum just before and just after, in other words, so that we have an isolated system, and we're going to find that that momentum just before and just after are going to be exactly the same. Remember, last week we were talking about impulse, the change in momentum of individual objects. That still applies. If we analyze the system, however, then we can't look at the change in momentum. We have to look at the momentum staying the same. Analyze an individual object within the system, you're looking at impulse. Analyze the system, or all of the objects combined, then you're looking at conservation of momentum. This idea that momentum stays the same. Now, I'll remind you what we said about impulse last week when we first introduced the concept as well. We said that impulse came from Newton's second law. If you remember, we derived the impulse equation from the mathematical expression of Newton's second law, F is equal to m times a. Today we're going to derive the law of conservation of momentum from Newton's third law. And Newton's third law, if you remember from physics 20, says if object 1 applies a force on object 2, then object 2 will apply an equal and opposite force on object 1. In other words, for every action, there's an equal and opposite reaction. That's Newton's third law, again, as opposed to impulse, which came from Newton's second law. Now, let's derive an equation from this. We're going to replace F12 with m times a. The mass of object 2, the acceleration of object 2, is equal to the force of object 1 on object 2. Of course, that's going to be equal to m1 times a1, where we stick a negative in front of it so that it's equal and opposite. Now, let's replace a, the acceleration, with delta v over delta t. So now we've got m times delta v2 over delta t2. Just a substitution for a is equal to delta v over delta t. That's equal to negative m1 times delta v1 over delta t1. Again, a substitution of delta v over delta t for acceleration. Now, we can actually cancel out the t's here, even though the first one is delta t2 and the second one is delta t1. The time of the collision, whether we're talking about object 1 or object 2, is the same. Therefore, if it appears in every term and it's the same value, we can cancel it out. So now we're left with m2 delta v2 is equal to negative m1 delta V1. Now, let's replace delta V with Vf minus Vi. So it becomes m times V2F minus V2I equals negative M1 times V1F minus V1I. Looks a little bit more complicated, but it's really the same thing. Delta V is Vf minus Vi. Delta V2 is V2F minus V2I. Now, let's distribute the mass inside the brackets here. Let's say M2 times V2F minus M2 times V2I equals negative M1 V1F. Negative M1 times negative V1I is positive, right? A negative times a negative is a positive. M1 V1I. Now we can swap places with some of these terms, and when we do, we end up getting an expression that looks like this. M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. Now what does that tell us? Now look, M1 V1I plus M2 V2I. If we have two objects colliding with each other, then the momentum of each object added together gives me a certain value, an initial momentum, a total initial momentum. If we look at the final term here, M1 V1F plus M2 V2F, after the collision, the total momentum of these two objects, PF we'll call it, is going to be exactly equal to the initial momentum. So in other words, the total initial momentum is equal to the total final momentum. That's just what we were talking about, the law of conservation of momentum. Total initial momentum equals the total final, if we have an isolated system, if friction and air resistance and all of those other forces haven't had a chance to act. Now, we have three problems that we're going to work on today, three sample problems, that is, that we're going to work on today. I want to do the first one, and then we'll let you work on a few questions from our worksheet. Example question number 1, which comes from the handout that you received at the beginning of class today. It says, a 1,500 kilogram car traveling north at 20 meters per second collides with a 1,700 kilogram car traveling south at 21 meters per second. We got a north and a south here. I want to circle those, draw attention to those, just so we don't forget to make one of them a negative. Now, these two cars, they collide with each other, and then they entangle, or they head off as one object after the collision. Maybe the bumpers entangled with each other to keep them together, or whatever it is, they're heading off as one object. We want to find out what the velocity of that wreckage is immediately after the collision. Now, technically, if we wanted to use impulse, we could pick one of these objects and go with it, using the concept of impulse. But what I want to do today is look at the whole system, both objects combined. If we're going to do that, then we have to use the law of conservation of momentum. Let's write down some givens here. We're going to say that M1 is equal to 1,500 kilograms. We're going to say that V1I, that's the initial velocity of object number 1, is 20 meters per second. It's to the north, so we're going to make it positive. M2 is 1,700 kilograms, and we're going to say that V2I is negative 21 meters per second. Negative because it's to the south. I didn't forget to write down the negative because I've got north and south circled to remind me to remember the negatives and positives. We're looking for VF. Not V1F, not V2F, but VF. There's only one VF because these objects have stuck together. One object after the collision, we'll just call it VF. Now we're going to say that PI equals PF. Remember, just a minute ago, that's the equation that we derived right here. The law of conservation of momentum, the total initial momentum equals the total final momentum. We have two objects before the collision occurs, so we're going to write down a momentum term, M1 V1I plus M2 V2I. write down a momentum term for each of those objects. The momentum of object 1 plus the momentum of object 2 before the collision equals, now, how many objects do we have after the collision? They stick together or they entangle, so there's only one. We're only going to have one term, therefore, after the collision, and that term is going to be MVF. Two objects become one object. Now let's sub in some numbers. M1 is 1,500 kilograms. V1I is 20 meters per second. M2 is 1,700 kilograms. And V2I, and this is where we got to be careful, but we're not likely to make a mistake because we circled in red and remembered when we wrote down our givens to make it negative 21 meters per second, equals, what's M going to be here? We've got one object that's made up of two different vehicles. The total mass here of this one object is going to be 3,200 kilograms. It's the mass of the car combined, the lighter car that is combined with the heavier car, times VF, of course. Now, 1,500 times 20 plus 1,700 times negative 21 gives me negative 5,700 on the left-hand side. Negative 5,700 equals 3,200 times VF. Take the 3,200 over by dividing, and we end up getting negative 1.8 meters per second. Or you could say, of course, 1.8 meters per second to the south. Can't say negative 1.8 to the south, because that would mean north. But it's either negative 1.8 or positive 1.8 to the south. So, what are the important things to remember here? Well, number one, you're using the law of conservation of momentum now, not impulse. So if you're using conservation of momentum, let's analyze the system. Remember, impulse was an individual object. Conservation of momentum is the system. Number two, let's get the signs straight. North and south, positive and negative. Number three, get the givens right. That's so critical in these questions. If you get these givens over here correct, then you're likely to get the rest of the question correct. PI equals PF, just sub in your numbers, and as long as you can do some math and you got the givens right, you're good to go. All right, what I'd like you to do now is have a look at worksheet number 3. There's a number of questions on that page, 7 of them, in fact. I'd like you to look at worksheet number 3, questions 1 to 3 for now. All right, let's have a look at another example. Example number 2. This one says a 0.0060 kilogram ball moving at 3 meters per second to the north collides with another ball that's exactly the same mass, 0.0060 kilograms, traveling 2 meters per second to the south. First ball moves off at 1 meter per second to the south immediately after the collision. What's the velocity of the second one? Well, let's circle north and south to remind us to account for the negatives and positives. What's similar about this question versus the last example that we did? Well, there's a collision taking place. Two objects collide with each other. What's different? Well, in the last case, the two objects collided, but they stuck together. In this case, they collide and bounce off of each other. That doesn't change things a whole lot, but you'll see the structure of the equation changes a little bit. Let's take a look at it now. Let's say M1, mass number 1, is 0.0060 kilograms. And let's say V1 initial is equal to 3.0 meters per second, positive because it's north. Let's say M2 is also 0.0060 kilograms, and V2I is equal to negative 2.0 meters per second, negative because it's to the south. So we're going to say that V1F, this is the first object, V1 final, because after the collision, right? V1F, it moves off at 1 meters per second to the south. We're going to say V1F is equal to negative 1.0 meters per second. And of course, we're looking for V2F. We're looking for the velocity final of the second ball. This should say second ball, not second car. All right, same deal as before, right? If we're analyzing the system, then we got to look at the system using the concept of conservation of momentum. We're going to say M1 V1 initial plus M2 V2 initial. This is the momentum of object 1 plus the momentum of object 2 before the collision equals. Last time we said MVF because the objects stuck together and they headed off as one object. But this time they head off as separate objects, so each one of them has to have a momentum. We're going to say M1 V1 F plus M2 V2 F, the momentum of object 1 after plus the momentum of object 2 after the collision has taken place. Now you might spot a shortcut here. We've got a mass of 0.006 for both objects, which means the same number appears in every term. Yeah, that simplifies things quite a bit. It means we can cancel out the mass. That leaves us a pretty simple calculation that we can probably do in our heads, actually. V1I is 3.0 meters per second. V2I is negative 2. We're not putting the mass in here because we canceled it out. V1F is negative 1.0 meters per second plus V2F. We could solve for V2F here, and when we do, it should work out to be positive 2.0 meters per second. Or you could say 2.0 meters per second to the north. So same deal as last time, right? Let's pay attention to the signs, positive and negative. Let's focus on the fact that we're analyzing the system and therefore using conservation momentum as opposed to analyzing one object and using impulse. Let's get our givens correct, and then it kind of flows from there. Pi equals Pf sub your numbers in. If you notice the canceling of the masses, that's great. It saves you some work. If you don't, that's okay. You'll still get the same answer. It just means a little bit of work in your calculator. We all should end up with the same number, 2.0 meters per second. All right, got a few questions for you to work on that relate to this example, also from worksheet number 3. This time I want you to work on questions number 4 and 5 at your desks, please. All right, last example of the day. This one says a 75 kilogram man is standing on ice while holding a 2.5 kilogram ball. He's standing, not moving. He's standing on ice holding a ball. The man throws the ball forward at 15 meters per second. What's the velocity of the man immediately after he throws the ball? So you know from physics 20 that if the man applies a force on the ball will apply an equal and opposite force on him. He throws the ball forward, he's going to move backward. We also know that he's going to move backward with a smaller velocity than the ball moves forward because he's heavier. Let's figure out what that velocity is. Let's say that M1 is 75 kilograms. That's the mass of the man. Let's say M2, the mass of the ball, is 2.5 kilograms. Let's say, pay attention to this, focus on this one here. Let's say that VI, not V1I or not V2I, because before anything happens, there's really only one object. It's the man and the ball combined. The man and the ball are one with each other. The velocity of that one object, that man-ball object, is 0 meters per second because he's not moving. He's holding the ball and he's not moving. We're going to say V2F, the final velocity of object 2, the ball, is 15 meters per second. And we're going to solve for V1F. That's the final velocity of the man. We already said that we expect V1F to be smaller than V2F. We would also expect V1F to be a negative value. If the ball goes forward, the man goes backward. When we solve this problem, however, the mathematics should show us that. We shouldn't have to write it in right now. The problem itself should show us. All right, so let's set this up the way we set up the other two examples, PI equals PF. This is not a collision, but this is what we call an explosion, right? Not literally an explosion, but it's like an explosion where one object becomes two. Momentum is still conserved as long as we have an isolated system. So we'll say that PI equals PF. The total initial equals the total final. Now, get a bit of a shortcut here, a little bit of a shortcut. This man is standing at rest. The ball is at rest with him. The total momentum of object 1, the only object we have, the man-ball combination, is 0. We could say M times VI, but we know that VI is 0, which means that PI is also 0. Save us from plugging in that expression and then doing some multiplication. After this explosion takes place, however, there are two objects, M1, V1, F, that's the final momentum of the man, plus M2, V2, F, that's the final momentum of the ball. Masses don't cancel this time like it did in the last example, because they're not the same value. M1 is 75 kilograms. V1F is what we're trying to find, the final velocity of the man, which we predicted would be smaller than V2 and a negative value. M2 is 2.5 kilograms times V2F, which is 15.0 meters per second. Solve for V1F here. When we do, it works out to be negative 0.50 meters per second. The ball was moving positive 15. The man moves negative 0.5. We predicted it should be smaller because the man's mass is bigger than the mass of the ball. We also predicted that it should be backwards. If the ball goes forward, the man should go backwards or negative direction. V1F is negative 0.50, or we could say V1F is positive 0.50 backwards. All right. I want you now to finish off worksheet number 3 that you've been working on earlier today. That consists of finishing questions 6 and 7. 7's a challenge question. Do your best on it. We'll take a look at it tomorrow as you guys finish all of these questions on the worksheet up for homework tonight.